welcome to P005, Work, Energy, and Power. These three concepts form one of the most powerful problem-solving frameworks in all of physics. Sometimes a problem that looks impossible using Newton's laws becomes trivial when you switch to energy methods. Today we will understand what work actually means mathematically, how kinetic and potential energy are defined, why the work-energy theorem is so useful, and what power tells us about rate of energy transfer. This is a high-weightage topic in NEET, so let us cover it thoroughly. Hook, carrying a heavy bag, are you doing work? Here is something that surprises every student the first time they hear it. Imagine you are carrying a heavy backpack across a corridor. Your muscles are burning, your shoulders are aching, surely you are doing work? In physics, the answer is no, or more precisely, you are doing zero work on the bag. Work is defined as force times displacement times the cosine of the angle between them. You are exerting an upward force to hold the bag against gravity. You are moving horizontally. The angle between upward force and horizontal displacement is 90 degrees. Cosine of 90 degrees is 0. So work equals 0. Your muscles are doing work internally, fighting against your own body's weight and inertia, but no work is done on the bag in the direction of its travel. Work is the transfer of energy by a force over a displacement. The cosine factor is critical, it is the component of force that is parallel to the displacement. Kinetic energy is the energy of motion, 1/2 mass times velocity squared. Notice the velocity squared term, doubling the speed quadruples the kinetic energy. This is why highway speed limits matter so much for crash safety. Gravitational potential energy is mgh, where h is measured from a reference level you choose. Elastic potential energy, stored in a compressed spring, is 1/2 times spring constant times extension or compression squared. These are the three main energy types you will encounter in NEET, and you must be able to switch between them fluently. The work-energy theorem is one of the most useful tools in mechanics. It says the net work done on an object equals the change in its kinetic energy. This lets you bypass force analysis entirely. Instead of solving differential equations or drawing free body diagrams for curved paths, you just compare energy at 2 points. Conservation of mechanical energy is a special case. When only conservative forces like gravity and spring forces act, total mechanical energy remains constant. Kinetic energy plus potential energy at point 1 equals kinetic energy plus potential energy at point 2. When friction is present, friction does negative work, removing energy from the mechanical system. Always account for this lost energy as W friction equals friction force times the distance over which friction acts. Let us solve the same problem two ways to show why energy methods are powerful. A 2 kilogram ball dropped from 20 meters. Using kinematics, v squared equals 2 times 10 times 20, giving v equals 20 meters per second. Using energy, at the top, all energy is gravitational potential energy, equal to mgh equals 400 joules. At the bottom, all energy is kinetic, half mv squared. Setting them equal gives v equals 20 meters per second. Same answer. But look, the energy method did not require memorizing which kinematics equation to use. For more complex problems, like a ball rolling down a curved ramp or a pendulum, energy methods are dramatically faster. This is why physicists and engineers default to energy analysis, it cuts through the complexity. Let me summarize all the key equations for this topic. Work is force times displacement times cosine theta. Kinetic energy is half mv squared. Gravitational potential energy is mgh. Spring elastic energy is half kx squared. The work-energy theorem connects net work to the change in kinetic energy. Power is the rate of doing work, joules per second, which we call watts. The formula P equals F times V is especially useful for vehicle engine problems. Efficiency, expressed as a percentage, tells you what fraction of input energy becomes useful output energy. For collisions, elastic collisions conserve both kinetic energy and momentum, inelastic collisions conserve only momentum, with kinetic energy lost to heat, sound, and deformation. The perfectly inelastic collision, where objects stick together, loses the most kinetic energy. Here is your NEET exam strategy for work, energy, and power. Conservation of energy questions are among the most common in NET physics, at least 3 per paper. The strategy is clean: identify the 2 points you are comparing, write down the energy at each point, set them equal if no friction, or subtract friction work if friction is present. For power questions, remember P equals W over T or equivalently F times V. These are often calculation questions with a direct formula substitution. The most common error is forgetting that work can be negative. Friction always does negative work. A force opposing motion does negative work. When you see a cosine theta in the work formula, ask yourself, is this angle less than 90 or greater than 90? Greater than 90 gives a negative cosine and therefore negative work. 5 key takeaways from P005. 1. Work equals Fd cosine theta, only force components parallel to displacement count. 2. Kinetic energy scales with velocity squared and potential energy with height. 3. The work energy theorem lets you skip force analysis entirely on many problems. 4. When no friction acts, total mechanical energy is conserved between any 2 points. 5. Power is the rate of energy transfer, and efficiency tells you how much of that energy is useful. In P006 we extend these ideas to rotational motion. Spinning objects have their own version of kinetic energy, and torque plays the role of force. See you in the next lesson.